Hello and welcome to this video. My name is Ramendu and I am working as a senior engineer with Uber. So in this video, we will learn about the time and space complexity analysis in the context of algorithms. So let's get started. So for any problem that we solve in computer science, we have to write some code for the same. And all the code that we write does consist of a set of instructions. So the way those instructions are arranged and the way those instructions are executed are called as algorithms. So you could understand, or probably you could visualize algorithms as something which is a kind of blueprint for a program for some sort of code. So before writing the actual code, what we do is we try to come up with certain steps that we will be doing. So essentially all those steps collectively which are there to solve a given problem is called as an algorithm. So you could understand algorithm to be a blueprint, to be a kind of plan of action, and when the same thing is implemented in code, it becomes a program. That is the actual code that is getting executed on your machine. So all the code that we write, it will have some sort of time and memory requirements. So what I mean by time and memory requirements is, even before we go into that discussion, let's assume that we have a problem P. So a problem could be solved using couple of approaches. So let's say there is a problem P and it can be solved using, let's say, solution 1, solution 2, solution 3 and solution 4. So for a given input I, all these solutions S1, S2, S3 and S4 are going to take some time. So let's say this is going to take time T1, this is going to take time T2, this is going to take time T3 and this one is going to take time T4. And based on the solution that we have decided, or rather that we have planned, we will be using certain data structures to facilitate the algorithm. So uses of those data structures, for example, let's say one of the solutions is going to make use of array, one of the solutions is going to make use of hash map, and so on and so forth. So based on your use case, whatever data structure is going to be used, that will lead to the space requirements, right? So essentially this thing is called as the space complexity, and the time taken by the solution is called as the time complexity. So this is the core idea behind the topic of time and space complexity. And usually what we do is, based on our requirements, we choose one of the solutions. So it can so happen that one of the solutions could be doing good on the basis of time complexity, but not so good on the basis of space complexity. Or there could be a solution which is the best in both the scenarios. So probably it's the best with respect to the time complexity and it's the best with the respect to space complexity as well. So depending on the use case, depending on the kind of solutions we have to take a call that which solution are we going to use. And finally, when we have the most optimal solution for a given problem, that becomes the candidate for the final implementation. So right from the problem statement till the time you have a final working solution that is the best in terms of space and time complexity within the given constraints is what referred to as the space and time complexity analysis for a given algorithm. So before we move ahead in the video and discuss some more things related to how we can find the time and space complexity for a given algorithm, we need to learn about something which is called as asymptotic notation. So let's learn about the same, which is asymptotic notation. Why is it called as asymptotic? I will come to this after some time, but for now please note that there are a couple of notations that we use to represent the time and space complexity. The first one is the big O notation. So big O. So essentially this is represented as O, like the letter O, right? And this one will contain certain function. So For example, it could be big O of n square, big O of n, big O of n cube, and so on, so forth. So what exactly is this function and what is the significance of it? Let's learn this. So let's assume that we have a graph, something like this, and this axis is the time taken axis, and this axis is n, where n could be the input size. So let's say we have a function fn which is growing like this, and essentially we have this as 0 and this as n. So at 0 it's going to take certain time, and at this particular instance it's going to take certain time, at this particular instance it's going to take certain time to run, and so on and so forth. So this is the graph that we have, and let's say this is represented by a function fn. And at the same time we have another graph which is like this, and this is called as c of gn. So essentially this graph is represented by c of gn. So what we can observe is that after a certain point of time, so let me use a different color here. So after a certain point of time, the c of gn is always bigger than this f of n. So no matter what, this c of gn is growing more or is always on the top of f of n. How we can represent this? So one way to represent this is like this. So we have function fn, then we have c of gn, and it's always greater than or equal to f of n after this particular point. So let's say this particular point is n naught. So if f of n is less than or equal to c of gn for a n which is greater than or equal to n naught, and for c which is greater than 0 and n naught is greater than or equal to 1, then in that case we can say that f of n is big O of gn. So I am assuming you might be finding this confusing as of now, but don't worry, we will do lots and lots of examples on this topic, and by the end of this video you would be very much comfortable into analyzing all these asymptotic notations for different algorithms. But anyway, continuing to our use case, so what we are essentially trying to say is that we have two functions f of n and g of n. So c multiplied by g of n is greater than or equal to f of n after certain conditions, certain constraints, and the first constant is this happens after we have n which is greater than n naught. So basically for all the n's which are after this n naught, so this is the first case. Second case is that c should be a positive number greater than 0. So this is the second case. So this can be any constant value, as in any non-zero value like 1, 2, 3, 4 and whatnot. And n naught should be greater than or equal to 1. It cannot be 0. So if this is the case, as in if there are two functions and you are able to find such n and such c and such n naught rather and such c, then in that case you could say that function fn is equivalent to big O of g of n. Before we move ahead with a couple of examples to understand to find such n and c values, let's understand why exactly are we going to need this notation. So what is the need for such notation? Assume that you are going to plan something. Then in that case, you may think of what are the different things that could happen. For example, let's say you have a plan to go out. Assuming that it's a rainy season, then you could plan for a couple of things. For example, let's say if you are going by motorcycle, then in that case, let's start like it's a rainy day and you are going by a motorcycle. So in that case, you could think that what is the worst thing that could happen? Well, it could rain, then maybe there are some couple of situations related to this constant, which is the rainy season, right? It could rain, that is the first one, or something else as well, probably you could imagine. So out of all these things that could happen, what is the worst thing that could happen, right? So if the worst thing that could happen is, let's say it's going to rain and you will get all wet and all those things that you don't want, then in that case you are kind of trying to bound your outcome or bound your activity under the worst thing that could go wrong, right? So let's say if you're going out and if it's a rainy season, and the worst thing that could go wrong, that it could rain and probably you will get trapped in that. So that is the worst thing possible, right? Beyond that, there is nothing worst that could happen. So the worst case condition is represented by the big O of whatever function you have, right? So you could be sure that in any case, this is the worst possible outcome. There is nothing more than that. For example, if it's the worst case is big O of n square, then at any given point, you will not have performance worse than this one, right? So that is the intention and intuition behind using the big O notation, which will give you the worst case possible outcome. Let's go back to the discussion that we were having. So maybe I will continue the discussion here. Let's assume that we have two functions. First one is, for example, 4n plus 2. And then we have a g of n, which is n. Then we are supposed to find out if f of n is big O of gn or not. So in order for this to happen, we will have to find out that f of n is less than c of g of n. And what are such c's? So the first condition is that this c should be greater than 0 and the n naught should be greater than or equal to 1. So let's start by putting certain values. So for example, we have 4n plus 2 and here we have cn. Then for what kind of c, I could have the c of n greater than or equal to this side of thing. So if I put c as 1, then what I have is 4n plus 2 and 1. This is definitely not the case. What if I put c as 5? So let's assume we have c as 5. So 4n plus 2 and this is 5n, right? So this was like not 1, rather it should be 1n, and this is 5n. Now that we have this thing, let's try to find out if we are able to find a n naught. So if I take this 4 in this side, then it will be 2 and this would be n. So we can say that n naught could be all such values which are greater than or equal to 2. So when we place this value in this above equation, it becomes 8 plus 2 and this becomes 10. So essentially, for all the values which are greater than 2 for n naught and c as 5, we are saying like 10 is definitely less than equal to 10. If I replace this with 3, then in that case we will have 4 multiplied by 3 plus 2 and 15. So this becomes 12 plus 2, that is 14, and this is 15. So what we find out is that for a given c which is 5 and n naught which is greater than equal to 2, for all such values we will have f of n less than equal to c of gn. And since we find out that this is the case for this particular c and n naught value, we can be rest assured and we can say that fn is indeed big O of g of n. And what is g of n? G of n is n, so fn is big O of n, right? So please note that now that we have established that fn is big O of n, all the values that will be greater than n would be definitely big O of n for the fn. For example, what is greater than n? It could be n square, n cube, n to the power 4 and so on, so forth. So definitely these are bigger than O of n. So essentially f of n is equivalent to big O of n square, big O of n cube, big O of n4 and so on and so forth. But it does not make sense to sort of use these values. Rather what we want is, we want the tightest upper bound. So what I mean to say is, let's say that this is our graph, and in this graph we can have this f of n, and we could have this as big O of n, then we can have big O of n square, then we could have big O of n cube and so on and so forth. But what we want is the closest one which is going to satisfy this criteria, this condition, right? So this criteria and this condition which is being satisfied for the closest one is going to be big O of n, and that is the reason our big O of n is going to be this itself, that is big O of n. So fn is big O of n. So that should be it about the big O notation. Now we will move to the another notation. Now let's learn about another asymptotic notation which is represented by omega, and it's also called as big omega. So essentially the way we represent this is with omega sign and whatever function is there to represent it. So like we saw in the earlier section, we will again draw a graph and try to visualize this. So let's have this graph wherein this is going to be the time axis, this is going to be the input size, and there is a function fn which is like this, and then there is another function, let's say c of gn. It's not c of gn, rather it's c multiplied by gn, cgn, right? So gn is the function and c is the constant. So what we see is that after certain time n naught, the value of f of n is always greater than or equal to the value of c multiplied by gn. So what we have here is quite opposite to what we had in the big O notation. So unlike the big O notation wherein we saw that fn was less than cgn, here what we are going to have is f of n is going to be greater than or equal to cg of n. So if we are able to find out a c which is greater than 0 and n naught which is greater than or equal to 1, for which this condition is satisfied, we can say that f of n is big omega of n, or big omega of g of n. Let's see an example and continue this discussion further. So assume that we have f of n as 4n plus 2 and g of n as n. So what we want to figure out is f of n big omega of g of n, and if this is the case, we want to find out the value of c and the value of n naught. So let's start by assuming that we are indeed having this condition satisfied, that f of n is greater than or equal to c of gn. So gn is nothing but n itself, and fn is 4n plus 2. So 4n plus 2 should be greater than c of n. So what happens when we are going to take the value c as 1? So let's say we have 4n plus 2 and this is greater than equal to 1n. So basically what we have done is we are choosing the value c as 1. So for all the values n naught which is greater than 1, so what I mean to say is for all the n naught which is greater than or equal to 1, this value is going to be satisfied. So let's say if we have n naught as 1, then what we will have is 4 plus 2, which is 6, and this is 1. So this is greater than this. If we have n naught, which is 2, then we have 4 2s are 8 plus 2 10, and this is going to be 2 basically. So this is greater than or equal to 2. 10 is greater than equal to 2. So what we found out is that for this condition to be satisfied, C should be 1 and n naught could be greater than equal to 1. So can we say that f of n is big omega of g of n, because we found such C value and n naught value. So f of n should be big omega of what was g of n? G of n was n. So big omega of n. And like we saw in the case of big O notation, that anything greater than that is also a big O notation, but we should be always taking the tightest upper bound. In this case as well, we can have anything less than this n as the big omega notation, but we should be always taking the tightest lower bound. So what are the possible values for this, which is lower than n? So it could be log of n or log of n, and so on and so forth. But the idea is, even though we could have multiple values which will be less than n, we should be always taking the tightest upper bound, which is going to be n. So here in this case, this line, this particular thing is the big omega of f of n. So like we saw in the case of big O notation, that it's going to tell us what is the worst thing that could happen. This big omega notation is equivalently going to tell us what is the best that could happen. So essentially, this is your best case scenario, best possible scenario, what would be the output, and big O is the kind of worst case possible scenario, that what is going to be the output. So before moving further to the next notation, let's compare these two, and which one is more practical to be calculated or to be analyzed in any of the algorithmic problems that we are going to solve, right? So on the one hand, you have big O notation, and on the other hand, we have big omega notation. So for all the practical purposes, we are always going to be interested in the big O notation. Big omega notation is good to know, but this is not going to help us into estimating our performance for the algorithm or the code we are going to write. So let's understand this with more concrete example. So let's say that you have a requirement wherein you want to sort a given array, and that array is quite big. So let's say you are going to use some sort of sorting algorithm. Let's represent that by SA, and depending on the kind of state in which the array is, as in is it partially sorted or is it like totally non-sorted, the outcome of the algorithm could differ. So let's say the algorithm is such that if the array is totally non-sorted, then in that case, the worst case possibility could lead to, let's say, a time execution time of t1 seconds. If the array is somewhat sorted, let's say there are two parts wherein like the two parts are individually sorted, then in that case, the time taken by this algorithm would be, let's say, if it's t2. So it would so happen that the time t2 would be less than the time t1. So what I mean to say is, since this array is somewhat already sorted, and since this array is totally non-sorted, the algorithm that we are going to apply remains the same, but due to the nature of the state of the array before sorting, the time taken is going to differ, right? And the time taken represented by the omega is going to tell us this particular time, this thing which is the best case possible scenario. What is the best case possible scenario? That the array could be already sorted. That is the best case possible. But in all of your practical purposes, is it going to be the case? Are you going to gain anything out of it? No, right? What you want to understand is, even though the worst case scenario is like your array is totally non-sorted, and in that case you want to evaluate that how exactly your algorithm is going to perform, right? So that is the reason we are always interested into finding out what is the worst case possible scenario and what is the worst case possible time performance. And we start with this worst case possible time performance and we try to improvise on that one or improve on that one. So for example, let's say there are two algorithms. Algorithm 1 is going to give me a time complexity of big O of n square. Algorithm 2 is going to give me a time complexity of O of n. So I know that both of these are worst case time complexity, but this is something which is better than the other one. So in that case, I'll be going with A2. Of course, there are many other factors in place. For example, what is the kind of space complexity we have and all those things. But having said that, this is the intuition or this is the differentiation behind these two time complexities, these two asymptotic complexities that we learned so far. And please note that till now I have been saying these things, these notations as like this is the time complexity, but the same notation applies to the space complexity as well. And we will see how it's going to be applied for the space complexity as well in the later section of the video. But please be rest assured that these are the notations and these are equally applicable for both the space and the time complexity. The idea and the notation remains the same. It's just that the metric that we are evaluating or analyzing, which is either the space complexity or the time complexity. Now let's learn about the third asymptotic notation, which is the theta or big theta. So it's written as theta of fn. Please note that this is not a very practically used kind of notation. So in that sense, I won't be going much deep into the explanation, but just for the sake of completion, let's complete it quickly. So assume that again we have a graph wherein this axis is the time taken and this is the input size, which is n. Let's assume that we have a function fn and then we have another function that is c of gn and another function which is, let's say, c of hn. Then after certain value of n, which is this, let's say this is n naught, and for some value of c, let's say some value c, we are going to have a situation cgn is greater than equal to fn and fn is, I'll write it here, greater than equal to c of hn. So if we are able to find such a c and such an n, then we can say that fn is theta of gn or fn is theta of n. And please note that this should not be h of n, it was a mistake, rather it should be gn. So g of n is the function. Here it's just that this is value c1 and this is value c2. So essentially we are supposed to find c1 value and c2 value and the value n naught such that this thing is satisfied. So that's about this theta notation. Now let's understand what is the significance of this theta notation. So in the case of big O notation, we saw that gives us a tighter upper bound. In the case of big omega notation, we learned that gives us the tightest lower bound. And in the case of theta notation, it gives us the tightest upper bound and the lower bound. So essentially, this thing is going to tell us what is the average case time complexity or space complexity for a given algorithm. Let's conclude this section on the asymptotic notations with a quick example. So first of all, let's write all the notations that we learned so far. So we have big O, then we have big omega, then we have theta. So this is the worst case, this is the base case, and this is average case, right? So assume that we have an array of numbers. So let's say we have 5, then we have 2, then we have 1, then we have 7, then we have 3. And what we want is, we want to find for a value v in this array, if it is present or not. And the algorithm that we have implemented is linear search. So essentially we are going over each index and trying to look up if a given value v is present or not. So what is the best case possible scenario? Let's say that your value v was 5 itself. So in that case, you would find that value in just one comparison, right? So here you would find that value to be present. So in that case, what you could do is you could write big omega of 1, like in one comparison or in constant time. So it does not matter how long or how large is your array, you are going to find the presence in just one comparison. So this is the best case complexity. What is the worst case complexity? Let's say your value is 7. Then in that case, you need to go through the entire array one by one, and only in the last you will find this value to be present. So you are doing n comparisons, and that is the reason we are going to write this as big O of n, because we are going to do n comparisons. So this is the worst case time complexity. What about the average case time complexity? So if you try to do a simulation and do some sort of amortized analysis, you would find out that for the case of linear search, it could be something like big theta of n by 2, which is equivalent to big theta of n. So please note that in all the asymptotic notations, we ignored the constant values. So we had this constant value of 1 by 2, we ignored it, and it's as good as writing n itself. But anyway, this is the average case time complexity, but as I told earlier that this is not very much used, and this is sort of rarely used, and the only thing that you should be concerned about is big O of n. So the key takeaway from this section of the video is that we are only going to be interested in finding out the worst case time complexity, which is represented by the big O. And in all the code that we are going to write and all the algorithms that we are going to come up with or we are going to learn about, we should be able to find out this particular thing, the big O. So with this, let's conclude this section and move to the next one. So now we will learn about the time complexity analysis of iterative programs. But before we start with the analysis of iterative programs, let's learn about one more thing. So we have been seeing this, that there is a keyword called as asymptotic. What exactly does it mean? And first of all, what exactly is the function that is represented? So let's say when I say that this is the time axis and this is the input axis, and let's say if the growth of the algorithm is like this, where this is f of n. So what does this mean? Well, what it means is essentially we want to know that how exactly is the performance of the program is going to vary with respect to time while we are talking about the time complexity when the input size increases. We are not interested in two smaller values. Rather, let's say if n is equal to 10 versus n is equal to 10,000, we are interested in knowing that what exactly happens to the time taken when the input size increases from 10 to 10,000. So whatever is the progression based on the increase of the input size, that thing is being told by the graph that we have with this function fn, right? So why asymptotic? So in mathematics, asymptote is a concept where we are interested into a value of a function at some very large value, so near to infinity value. So let's say if there is a function which is represented by some sort of graph, then let's say if this is the initial value range, and this is the another known value range, then for all the values which are greater than the known range, let's consider that as infinity. So whatever is the value for the function in the infinity range is called as the asymptotic value. So let's say if the value is t, then this is the asymptotic value of the function fn, right? And that is the reason we call these notations as the asymptotic notations. So to simplify and to understand it in much more short and concise manner, please note that asymptotic notations will tell the performance, relative performance, rather an approximation of how exactly is your program going to perform with respect to the time taken at a very large value, and more so how exactly is your performance of the program is going to change once the input size increases, right? So that is the reason the value for fn is kind of an indicative approximated value. It's not something which is exact value. So fn is never going to tell you that it's going to be 5 seconds or it's going to be 2.7 seconds or something of that sort. What exactly it's going to hint is, let's say when we say fn is big O of n, then we can be sure that it's going to increase linearly with the increase in the input size, and the increase in the time it takes is going to be linear. When we say that it's big O of n square, then you can imagine the quadratic function graph, which is going to look something like this, right? Or maybe much lesser step, right? Maybe it could be something like this. So this is how the time taken by the code is going to increase when we increase the input size. This is my input size, this is the time taken. So this is what we mean by the asymptotic notation. So yeah, so with that in place, now let's move to the other part of the discussion. So any algorithm that we write in computer science could be expressed into a couple of fundamental steps, right? So basically the algorithm is going to be a block essentially. It could consist of sub blocks as well, but idea is that there is a block in which there is a scope in which you do certain steps. Those steps would be of course translated to a code, but for now assume that this is kind of a flow chart. This is kind of a step by step process. So this is your algorithm. So while doing so, you will have two kind of statements. So there would be certain statements which will be kind of just one liners. For example, let's say when you say we have print something, or let's say you are declaring some variable, so let's say int x is equal to 5. These are one liner statements, right? And then there could be a combination of loops. So for example, you could be writing something like a for loop or maybe a while loop depending on the language, but the idea is that your algorithm is going to have some sort of block wherein you will wish to do something repetitively over and over again based on certain condition. And the other is the conditional part, like if else kind of thing, right? So essentially the component which leads to the time complexity is the for loop, right? Or whatever loop you are going to write in your code. And the one liners are not going to contribute sure, they are going to lead to certain time consumption in the code when it's actually implemented. But remember, I told you earlier that asymptotic notation is about understanding how exactly is the time taken by the algorithm change when we increase the input size, right? And of course, when you have just like these statements are not dependent on the input size. So let's say for example, we have a function and the first one is to print some value, and then there is a loop which is going to run from, let's say, int I till n, and n is what we are passing in this function, and there is some operation that we are doing inside the loop. So of course does not matter whether your n is 5 or n is 10,000, print is always going to be printed just once. But this particular thing, since it's running from 1 till 10,000 or 5, it's going to depend on this particular value n, that how many times this thing is going to be executed, right? So this is something that is going to contribute to the time taken for an algorithm when the n size increases, the input size increases. So with this in mind and with this in place, let's learn about this thing, that any particular algorithm will be of course consisting of, let's say for the sake of simplicity, one liners. Then there would be certain looping constructs. Then we will have recursive calls. So looping constructs could be also understood as iterative calls. And except this, both of these two are responsible for leading to the time taken by your algorithm in the calculation for the time complexity. So essentially, when we talk about figuring out or calculating the time complexity of a program, we are supposed to find out what happens in the case if there is a loop or if there is a recursive call. So we will be discussing about how we can figure out the time complexity in the case of recursive constructs. But as of now, let's focus on how we can sort of figure out the time taken or the time complexity where we have iterative calls. And please note that any code which can be written using the iterative manner could also be written using the recursive calls or the recursive manner. So it depends on the kind of problem you are trying to solve, but there is no sort of discussion regarding which one is better or which one is not better. So depending on the use case you have, you could either go ahead with the looping approach or the recursive approach. So now let's focus our discussion to calculation of the, or rather the analysis of the time complexity for iterative programs with a few examples. So here we have the first question. So this is like there is a function called as fun, and inside the function we have a for loop which is going to run from 1 till n, and inside the for loop we have a statement which is just printing hello. So in order to calculate the big O time complexity for this function, what we will do is we will start looking inside the function content one by one. So first we see that the function signature is there. Then we see that there is a for loop, and other than that we have the closing. So of course this and this is not going to contribute to the time complexity. So let's focus on the for loop. So when we say that for loop is going to run from I as 1 till n, then in that case how many times this thing is going to be executed? Well, it's going to be executed n times. And inside the loop what we are doing is we are just printing hello. So this is something which is not dependent on anything, right? So it's just a print statement. So it has a constant time complexity which is big O of 1. We multiply these two. So essentially what we have is big O of n as the time complexity for this function method. Now coming to the next example, here as well we have fun method, and again we don't have anything else other than for loop, but this time there is two parts to the for loop. First part is the external part, wherein this thing is going to run from 1 to n, and then there is an internal part which again is going to run from 1 to n. So the way it works is like this outer thing is going to run n times, and for each and every time this inner thing is going to run as well. So essentially what we have is there is a condition wherein we have a loop, and there is another loop which is dependent on the outer loop. So for each and every time this loop is going to be executed, is going to be iterated, the internal loop will also be executed. So let's say for 1 it will be executed n times, for 2 it will be executed n times, for 3 it will be executed n times. So essentially what we are looking at is like on for the outer loop, on for the inner loop, and effectively we have big O of n square as the total time complexity. What happens if we have another loop inside this particular for loop, so let's say if I put another for loop inside this one, then in that case this will become big O of n cube. So you get the idea. And what if I place another for loop after this particular line? So let's say I erase this. So let me erase the other things as well, so it's sort of more clear to understand. So here is the closing part. Let's get rid of this one, and here again I am going to put another loop. Let's say k as 1 till n, and then there is some print statement. So what is going to be the time complexity? So think for a second. So for sure this part we have already discussed, that it's big O of n square, and since this loop is not dependent on either of these loops, and in fact it's well pretty much outside the outer for loop scope, so this will be executed separately and it will lead to the time complexity of big O of n. So speaking of the entire time complexity of this particular method, what we have is big O of n square plus big O of n. And as I told earlier, that when we are dealing with the time complexity notations, we always take the one which has the higher power, which has the higher value. So out of these two, which one has the higher value, higher power? Of course this one. So our effective time complexity is going to be big O of n square. So now let's move to the next question, which is this one. So in this we have a function called as fun, and then we have two values, one is I, other is s, both are 1 to begin with, and then there is a while loop. So what this while loop does is it will keep on running till the time s is less than equal to n, and inside the loop we have I which is getting incremented by 1 every time, and we have s which is getting incremented by the I value, right? And then we have a print statement. So this is something wherein we are not seeing a linear increase in the value, so we cannot say that this is running like for n times, so the time complexity is going to be big O of n. Rather it's depending on the I value, right? So essentially s should be less than n, and the value of s is depending on I, and I itself is getting incremented by 1 in each of the iterations. So let's analyze it further. So let me write the values for s and I here. So to begin with, s is 1, I is 1, and in the next iteration I becomes 2 and s becomes s plus I. So s is 1 and I is 2, so the value becomes 3. Then in the next iteration I becomes 3 and s becomes I plus s, so s is 3 and I is 3, so this value becomes 6. Then for 4 likewise we will have this as 10, for 5 we will have it as 15, for 6 we will have it as 21, for 7 we will have it as 28, and so on so forth. So where do we stop? Well, we stop only when the s value becomes greater than n. So this is going to run till the time it's less than equal to n. So when does it stop? It stops when it becomes greater than n, right? And assume that at value k, so I is also increasing, right? So let's say at some point of time I becomes k, and during that time itself it's going to become greater than n, and that is where it's going to stop. So if you look at the pattern very carefully, you will find something. So let me get rid of this line so that I could demonstrate in much better manner. So initially I and s both are 1. Now in the next iteration s becomes 3. What exactly is 3? It's 1 plus 2. In the next iteration s becomes 6. What is 6? It's 1 plus 2 plus 3. In the next iteration s becomes 10. What is 10? It's 1 plus 2 plus 3 plus 4. So essentially all the values at ace are the sum of first k natural numbers. So essentially what we mean to say is when k is 4, when I is equal to k and k is 4, then s is going to be 1 plus 2 plus 3 plus 4. So for I at value k, s could be represented as k plus 1 multiplied by k divided by 2. And at k, we are observing a value which is going to be greater than 1 in order for this loop to be terminated. So basically, k would be k multiplied by k plus 1 by 2, and it should be greater than n, of course. So when we calculate it, it's going to be k square plus k divided by 2 greater than n, and taking the most significant value in this one, which is k square, is greater than n, and when we calculate k, it becomes root of n. So what it means is that it's going to be executed k times, because k is the value at which it becomes greater than n, and when it becomes greater than n, when s becomes greater than n, that is where we stop. So what is the k value? K value is root of n, and since it's going to be executed k times, so the time complexity is going to be big O of root of n. So see, by looks of it, it was very difficult to figure out what exactly is going to be the time complexity in this case. But when we started to analyze the relation between s and I, we found a pattern. So there could be certain cases like this wherein it won't be very much straightforward to figure out the number of times the loop or a code block is going to be executed. So in those cases, you could resort to something like this. Probably you could try to figure out a pattern or something similar wherein like how many times a particular section is getting executed, and that will tell you what is the time complexity for that particular block. Let's have a look in this question. So here we have a function called as fun, and we have a loop which is running from I as 1 to n. Then we have another loop which is inside the first loop, and that loop is running from j as 1 to I. And then we have another loop which is inside the second loop, and this is running from k as 1 to 100. And in the innermost section, we are printing some message which is hello. So we need to find out what would be the time complexity in this case. So essentially what we wish to find is how many times this thing is going to be printed or executed, and that would be our time complexity effectively. So if we look closely, this thing is not depending on anything, as in does not matter what is the value of I or j, it's always going to be printed 100 times, that is 1 to 100. However, j is going to depend on the value of I, and I of course is changing from 1 to n. So let's formalize this. And let's write it here. So essentially we want to capture how many times this thing is going to be executed, printed. So for I as 1, j would be 1 and k would be 100 times. So this is going to be printed for 100 times when this is the case. Then we have I as 2, j becomes 2, and k is going to be printed 100 times and twice, because this thing is going to be printed twice, right? Rather, this thing is going to be executed twice, and eventually this will be printed 100 times no matter what. So 2 into 100, correct? Then for the next case, we have I as 3 and j as 3, and k would be 3 multiplied by 100, that is 300 times. So if we generalize it to, let's say, I as n, j would be n, and k would be n multiplied by 100 times. So how many times this thing is going to be executed is sum of this value, this value, this value, this value, whatever, and this value. So let's find it out. So we have 100 plus 2 multiplied by 100 plus 3 multiplied by 100 dot dot dot, then n multiplied by 100. So we can take 100 as common, then we have 1 plus 2 plus 3 plus n, and this is nothing but n into n plus 1 divided by 2, and eventually we will have 100 n square, like taking the most prominent part of this equation. So it will be of course n square plus 1 divided by 2 and whatnot, but n square is the leading term and 100 is the constant, so we can write this as n square. So eventually this thing is going to be printed n square times, right? And rather this thing is going to be printed these many times, and what we can say is the running time complexity of this algorithm is going to be big O of n square. Now let's have a look in this question. So what we have here is again a function called as fun, and we have 3 loops. The first loop is going to run from I to I as 1 to n. The other loop is inside this first loop, and this thing is going to be running from j as value 1 to I square. And then we have another loop which is inside the second loop, which is going to run for value k as 1 till k is less than n by 2. So this is the kind of a structure we have. So this is like we have the outer loop, then this loop, then this loop, and inside the innermost loop we are printing a message, press the bell icon. Thank you. So let's analyze what is going to be the time complexity for this one. So as always, our end goal is to find out how many times this message is going to be printed. And how do we find it out? So we start by substituting certain values for I, j and k and see how it's coming up, right? So let's do the same. So we have I as 1, then in that case j would be running till 1 cross n, remember, till I square times, and k would be running n by 2 times. So k does not depend on any value such as I or j, or whatever your value is for I or j, it's always going to be printed n by 2 times, right? So k is going to be printed n by 2 times, and eventually this is inside this loop, and this is getting 1 cross 1 times, so this will be printed totally 1 times, right? Then we have I as 2, j becomes 4, k is like 4 cross n by 2 times. Let's see for I as 3, j is 9 and k is 9 cross n by 2 times. So likewise at I as n, j becomes n square and k will be printed n by 2 multiplied by n square. So eventually k is the value, so these many times this thing is going to be printed. So what we want is, we want to find the total number of times this thing is getting printed, and in order to do that we will be adding these values, which is this value, this value, this value, so and so forth, and this value. So let's do it. So we have n by 2 plus n by 2 cross 4, then we have n by 2 cross 9 dot 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 n by 2 cross n square. So when we simplify it, we take out the n by 2 part, and we have 1, we have 4, we have 9, we have dot dot dot, we have n square. So when we find what is the formula for finding the first for finding the sum of first n, for finding the square of the first n natural numbers, this is the formula we have. So n by 2, and the formula is n into n plus 1 to n plus 1 divided by 6. And when you simplify it, we have 1, 2, 3, 4. So basically when you multiply it, it will be in magnitude of n to the power 4 something something something, which is essentially some constant but less than n to the power 4. So n to the power 4 is the most significant part of this equation, right? The running time complexity for this algorithm is going to be big O of n to the power 4. Now let's analyze the time complexity of this code snippet, and this is a sort of important pattern that you should pay attention to. So what we have here is a method called as fun, a function fun, right? And we have a loop which is running from I as 1 till I to n. But the steps in which I is getting incremented is different. So in the earlier videos, in the earlier questions rather, the assumption was that I is increasing in terms of 1 because we had like this implicit increment operation which is I plus plus. But here instead of this, what we have is I is incrementing by 2 each and every time. So what would be the time complexity in this case? So let's analyze this. The very first thing is that we want to figure out how many times this message is going to be printed, which is like this video. And the way to analyze this is again do this thing like where we put the value for I and see how many times this is going to be executed. So we will follow the same approach. So let's say we have I as 1 to begin with, and then I becomes multiplied by 2, which is 2. Then I becomes multiplied by 2, which is 4. Then I becomes multiplied by 8, and so on and so forth. At some time it becomes n, right? So what's happening here? This is the previous value and this value is multiplied by 2. This is the previous value, so this value will become multiplied by 2 for this value. So 2 cross 2, 4, 4 cross 2, 8, and so on and so forth. And at some point this becomes n. And what we want to figure out is that how many times this thing is going to be executed. This thing is going to be printed. So let's assume that this is going to be printed k times. So if we were to find a pattern to it, the way we say this is, let's say this is 2 to the power 0, 1, 2 to the power 1, 2, 2 to the power 2, 4, 2 to the power 3, 8. So let's say at value k, like if it's going to be executed k times, then at value k we have n. So let's say 2 to the power k, it should be n, right? So what we see is for 2 to the power k, value becomes n, and we are interested into finding k. So how can we find k? So simple mathematics will tell you that we can write this as k equals log to the base 2 value n. So this is the value of k, and essentially this thing is going to be printed these many times, and we can write it as big O of log base 2 to the n. So this is the time complexity for this use case. Now let's extend it, and here what we saw is that I is getting incremented in multiples of 2. What if it becomes 3? Then in that case we can see I as becoming like I as 1, then 3, then 9, then 27, and so on and so forth. At some value it becomes n, and we want to find that some value. So let's say at value k it becomes n. So this is again 3 to the power 0, 3 to the power 1, 3 to the power 2, so on, and 3 to the power k, and this value becomes n. So when we do this like 3 to the power k is n, and we wish to find out the k value, it again becomes log n to the base 3. And this is our runtime complexity. So the pattern to note here is that when you have a loop like this and it's getting incremented in terms of, in multiples of, let's say value k, then your time complexity is going to be log to the base k value n, where n is the maximum number of items, or basically where n is till the point I could reach. So this is your time complexity in a much generalized manner for this kind of loop condition. So let's analyze this question now, and what we have here is a method named fun, and we have 3 loops, the first loop is going to run for n by 2 times, that is I as n by 2 to n. The second loop is going to run from j as 1 to n by 2, that is again n by 2 times. And the innermost loop is going to run for k as 1 till k is less than equal to n. And the steps in which this thing is going to increment is multiplied by 2 every time, right? So before we move ahead in the video and analyze what is the running time complexity, I want to bring your focus to one observation. So here what we see is that I is running from n by 2 to n. J is running from 1 to n by 2. K is running from 1 to n. So none of the loops are dependent on each other. But in the earlier cases, what we were seeing is that, for example, so let me write it like this. So let's say if I was 1 till n and the inner loop was most likely j as 1 to j less than I, or till j is less than value I, right? So, and then there was something which was not dependent on it entirely. So what we had was, like, we had to unroll the dependent loops. So basically we were trying to find out for value I as 1 how many times this thing is going to run, and based on that combined value we were multiplying how many times this loop was going to be running. Essentially we did not bother about the inner loop because this was going to be executed a fixed number of times regardless of the fact what is the value of I or j. It was going to depend, of course, on the number of times this loop is going to be executed, but this loop as such was not depending on any of the outer loops for deciding that how many times this thing is going to be executed. So what I mean to say is that when we have this kind of dependency, we had to unroll the loop, wherein we had to kind of put certain value for I, then figure out the value of j, and then k was like, let's say if the value for this one was v, then the k, if the constant value was c, then this was going to be executed c into v times. So this is the kind of approach we had in the previous questions, where we had some sort of dependency between the loops. So let me erase this and then we will talk about this particular problem at hand. So what is the pattern we see and how we can solve it? So what we see here is that there is no dependency as such that we saw earlier, right? So this thing is going to run n by 2 times. This thing is again going to run n by 2 times. And as we learned in the previous video, that when we have this kind of incrementing operation, the time complexity is going to be big O of log n to the base increment value, that is 2. And since we don't have any sort of dependency, we don't need to unroll the loops. Rather, we can just multiply these values, which is n by 2 multiplied by n by 2 multiplied by log n to the base 2. So when we multiply all these three, we have the running time complexity in terms of n square log to the base 2 n. So this is going to be the runtime complexity for this code snippet. So two things you can take from this particular example. First is like we don't have any dependency among the loops. So in such cases, when we don't have dependency among the loops and they are inside each other, that is like there is an outer loop, then there is an inner loop, and then there is another loop that is inside the second most loop, then in that case we can just go ahead and multiply the number of times those loops are going to be executed. And the second thing is, if there is a dependency, then we have to figure out the steps in which these things are going to increment, and that is where we substitute the value for I, then we find out the value for j, and we find out the value for k, and then whatever value we find for the innermost loop, that is the k value, we add those values and try to figure out what is its dependency in terms of n, and that is going to give us the runtime complexity, which can be anything like whatever, right? the examples basically that we saw earlier. So these are the two key takeaways from this example, and this is the runtime complexity for this particular code snippet. Let's have a look on this question, and this question is going to teach us a very important model. So let's get to it and analyze. So what we see is that we have a function fun, and we have a while loop which is going to run till the value of n is greater than n, and inside the while loop we are doing this execution wherein we are dividing the value of n by 2. So let's say to begin with, n value is 2. So when we enter and execute this thing, let's say we do the execution, and when we come out the value becomes 1. Why? Because of course we are dividing it, right? So this becomes 1. And is 1 greater than 1? No, right? So in that case we can say that this got executed one time. Let's increment the value of n to be 4, and then we enter inside the loop, we execute it, we multiply by 2, it becomes 2. 2 is certainly greater than 1. Then again we are going to enter inside this particular loop, this section, and we are going to divide it by 2. The value becomes 1. 1 is not greater than 1. Then we can conclude that this thing got executed 2 times. Similarly, now let's try to put value 8. So we have one execution wherein we divide it by 2, the value becomes 4. We enter and execute again, we divide it by 2, the value becomes 2, and again we enter inside the loop, we do the execution, we divide it by 2, the value becomes 1. Now 1 is not greater than 1, so we can say that this got executed 3 times. So the pattern that we see over here is when 2 to the power is 1, then it's going to be executed 1 times. When 2 to the power 2, this is going to be executed 2 times. And when 2 to the power is 3, this is going to be executed 3 times. So we can conclude that when n is a power of 2 and the value of n is, let's say, 2 to the power k, then it's going to be executed k times. So what I'm trying to say is, if this n value is a power of 2, and let's say if that value is 2 to the power k, then this execution is going to happen k times. So we have this relation, and we need to find k. Then in order to find k, we can simplify this and write this as log to the base 2 n, and this is going to be the time complexity in this case. So you may ask, what if n is not a power of the 2? What does happen in that case? So let's generalize that with another example, and let's assume that we have n as 20. So we have n as 20 and we are going to enter the execution. We divide by 2, it becomes 10. Then we again enter the execution, we divide this by 2, it becomes 5. We again enter the execution, we divide by 2, it becomes 2. We again enter the execution, we divide this by 2, it becomes 1. Now 1 is certainly not greater than 1, so what we could conclude is that this thing got executed 4 times, right? So we can write this as log of 20 to the base 2. So since I know this, I am writing this, but you could just verify and check on your own. So this is something like 4 point something something. So this is like a base of, or rather a floor of, log of 20 to the base 2, and this is going to be our runtime complexity. So are we seeing any pattern here? Well, the pattern is that since we are dividing by 2, we are having this log of n to the base 2. What if we were dividing it by, let's say, k? Then what happens in that case? Well, in that case, we could say that log of n to the base k of floor of, so this is going to be our runtime complexity, And this is an important pattern. Probably you could note it somewhere and try to revisit it one more time. So this is what the time complexity is going to be for this use case. So in this case, you could just replace k with 2, and to generalize, this is how this is going to be looking like. So let's analyze this question. This is a bit interesting. So let's do it. We have a function fun and we have two loops. The outer loop is running from I to n and it's incrementing one by one, that is I plus plus. Then the inner loop is running from j as 1 till n and the j value is incrementing with I. So let's say if I is 1, then j becomes j plus 1. If I is 3, then it becomes j plus 3. So, and the inner loop is going to print something, as in how is the explanation, tell in the comments below. So what we see here is that I is incrementing in some fashion, then j is incrementing in another fashion, and that is dependent on the value of I. So we are seeing that it's a case of dependency. So as we saw previously, that whenever the loops are dependent on the outer loop, then we need to unroll the loops, and the way we do this is we put for the value of I and then we try to find out the value of j, and eventually we follow the same pattern and we try to find out how many times the innermost statement or the innermost execution is going to happen. So let's do the same. We start by putting the value of I as 1 and j is going to be running like 1 to n times, and of course j is going to increment by 1 because I is 1. So this will be executed 1 to n times and it's incrementing by 1. Then this inner thing will be getting executed, this inner block will be getting executed n times. Now let's try with another value, that is I as 2. J is going to run from 1 to n, but this time j is incrementing by the value 2, right? So j is basically j plus 2. So in the earlier case, when it was incrementing by value 1, it would have been executed n times. Now the value is incremented by 2. So it will be running twice as fast. And what it means is that the execution will be halved, right? So if it was earlier n, then now this time the execution would be n by 2 times. Likewise, we have I as 3. J is again going to be there for 1 to n, but j is going to be incremented by the value 3, by the value I, right? So again the execution is going to be 3 times faster, and what it means is it will be executed only n by 3 times. So when we extrapolate it to, let's say, some value I as n, then what we see is I is going to be n, j is going to be from 1 to n, and the execution will be happening just once because n by n times. So we have seen that it's going to be executed n times, n by 2 times, n by 3 times, so and so forth, and finally n by n times. So let's sum it up and find out what is the output. So n plus n by 2 plus n by 3 plus n by n. Let's take n as common. So we have n, we have 1, we have 1 by 2, we have 1 by 3, and we have 1 by n. And this thing is nothing but log of n. So essentially what we have is n log n, and the runtime complexity for this particular code is going to be big O of n log n. Now that we have learned how we can do time complexity analysis for iterative algorithms, let's learn how we can do the time complexity analysis of recursive functions or recursive algorithms. So first have a look on what exactly is the structure we have in the case of recursive functions. So essentially there would be a function, let's say it's called as fun. There is an input to it which is n, and based on certain condition, which is your base condition, we are going to return some smaller value, or rather we are going to call the same function recursively with certain smaller value. For example, let's say if there is some condition which is getting satisfied, what we are returning is we are calling the same function fun with value n by 2 plus the same function fun with the value n by 2. So in this condition, in this case, we don't really know how many times this thing is going to run, because this is going to depend on the base condition that you have, and you don't really know till the time the base condition is met how many times this thing will be executed. So the way we do the analysis for the recursive functions or recursive methods is very different from the way we were doing it for the iterative algorithms. So the first step that we do is, well, before we go to that, there are three approaches to do a time complexity analysis for the recursive algorithm. The first one is called as back substitution. That is what we are going to see now. So this one is back substitution. The second one is tree method. So basically we draw a recursive tree and we do the analysis. And the third one is the uses of the master's theorem. So in this video, maybe I will not be covering the master's theorem, because essentially it's just a bunch of formula that you could look up and you could try to do it yourself. There is nothing that I could cover, because the whole point of covering this master theorem is if I were to prove it, that why and why exactly this is going to work. But I feel that that could be somewhat out of a scope of this video. But if you're interested, you could have a look in the CLRS book. Coming to the topic, we have these three methods, that is back substitution, tree method, and the master's theorem. Now we will have a look on the back substitution. So in order to work with the back substitution, what we do is we try to translate the recursive algorithm to a recurrence relation in terms of the time taken. So let's say that the time taken to execute this fun n function with value n, or with the input n rather, is tn. And what we can say is, let's say if the condition evaluation is going to take a constant time c. Why it is going to take a constant time? Because this is just a condition evaluation, and this thing is not going to depend on the size of the input. In fact, there is no recursive call which is happening here. This is just a condition evaluation. So c time, and in order to evaluate two more recursive calls, that is this one and this one, we are still going to take some time t. And what that some time t would be? That would be n by 2, right? Because let's say if for this one we are going to take t of n, then for this one, which is half in size, we are going to take tn by 2 plus tn by 2 for the other half. So effectively this would be c plus 2 multiplied by t of n by 2. And this is going to be our recursive or recurrence relation in terms of the time taken. So with the help of the back substitution, what we need to figure out is how many times this thing is going to be executed. And of course, other than this recurrence relation, we will also have a condition regarding the base case. So there would be some base case value which will restrict in some way or the other. So as of now, it might sound a bit abstract, but next we are going to see certain examples using the back substitution method, and we would cover how exactly we can do this part. So let's do the examples now. So let's have a look on this example. So here we have a function fun. It's taking an input of n, and the base condition is if the value of n is greater than 1, then we are going to call the function fun recursively with the value n minus 1. So we are reducing the value by 1, and this thing is going to happen for the time being till which we have n is greater than 1. So since we are solving it using the back substitution method, the first thing that we are going to do is we are going to represent this in terms of time complexity recurrence relation. So let's say if the value is tn to represent the time complexity of this function fun n, then let's say this condition is going to take constant time c, and in order to execute this, we are going to take t of n minus 1. So this is what we saw earlier, right? if the time is going to take tn for the entire method, then for the smaller value, that is that is n by 2, the new time complexity that will be incurring is t of n by 2. And this is what we have done here as well. So usually we write the constant time c as 1. It does not make a difference, but on the same part it makes our calculation easier. So we can write this as t of n minus 1, and this is eventually t of n. So we need to find out what is the big O complexity, what is the runtime complexity of this one. So here is what we do in the case of back substitution. What we will be doing is we will be trying to find out the value of the recurring field, the recursive field, right? So this is the recursive field, that is t of n minus 1. And what I mean is that we need to find out the value of this one. So like we had the value of tn as 1 plus t of n minus 1. So we need to find out tn of value of n minus 1 or t of n minus 1. And in order to do that, we will be placing this value in this function, this particular method, or this function rather. So that is the reason this is called as back substitution. Eventually we are just substituting the value backwards in the main function. So what we get is 1 plus t of, and in place of n we place n minus 1. So n minus 1 minus 1, and this one becomes 1 plus t of n minus 2. Now this is what we have gotten for t of n minus 1. And now that we have t of n minus 2, we want to find the value of t of n minus 2 as well. So we follow the same thing. We substitute this value in this one. So 1 plus, and we will be placing n minus 1 into this one. So this will become n minus 1, n by 2, and eventually we will get t of n minus 3. So t of n minus 2 is 1 plus t of n minus 3. So there is a mistake that I did earlier. Eventually what will happen is, in order to find out the value of t of n minus 1, we will be also adding the one part, right, that I missed earlier. So there would be 1 as well. So 1 plus, there is 1. So let's say what I'm trying to say is t of n is 1 plus t of n minus 1. I replace the n part with n minus 1. So this of course remains, but when I find out that tn contained the one value, so that one value would be there. And now that we are finding the value of t of n minus 1, it will also bring its own constant. So the way to visualize this is, when we make the recursive call the second time, the other time, it of course will incur some constant condition check time, right? Which we are representing with either value c or value 1. So that is what is happening when you are replacing this value with n minus 1. So this thing basically becomes, let me erase this and write it more clearly. So this thing becomes 2 of ta of n minus 2, and of course this will become 3 because we are adding 1 to it. And let me erase this one as well. This is 3 plus t of n minus 3. So we keep on doing this act of back substitution. Let's say at some time when we have this thing as k, then we get like k plus t of n minus k, right? And what we want is that we want this thing to stop. Eventually we want to end into a state wherein we don't need to call this recursive call again and again. And when does this happen? Well, this happens when we hit the base case. What is the base case? Let's have a look. So this thing is going to be executed when n is greater than 1. So what we are going to execute? We are going to execute tn plus 1 plus t of n minus 1 whenever n is greater than 1. What happens when n becomes less than this condition? So what is not greater than 1? Let's say the closest value is 1 itself. So of course 1 is not greater than 1, right? So in that case we can substitute this, and this will become 1 minus 1, which is 1 plus t of 0. What it means is, you don't have any particular input to act on, the size became 0, and that is the reason you have this as the base case, as in you don't have anything to call on, and eventually this condition is not met, so you don't call anything, and eventually you will have the time complexity as, so basically t of 1 becomes 1. So if we want this thing to stop, what we want is this thing to align with this thing, right? So basically we want to hit the base case. And when do we hit the base case? When this t becomes 1. And when this thing becomes 1, so when we say that this becomes 1, then n minus k should become this value, right? N minus k as 1. So for what value of k this is going to become 1? So what we do is we take k on this side and we bring 1 on this side. So basically this will be n minus 1. So for the value of k, that is n minus 1, this thing is going to become 1 and we are going to hit the base case. We will replace this. So basically we will replace k with n minus 1 and then we replace n minus, and k is n minus 1, so it becomes minus n plus 1. So basically we replace k value with n minus 1 here. This is n minus 1, this is t of 1, and t of 1 is constant anyway, so n minus 1, and this is 1. So eventually we have n, and the way we could represent this is, this could be represented as big O of n. So essentially all this recursive algorithm or this method or this function that we had, which was represented as this recurrence relation in terms of time complexity, we started backfilling the values. So essentially we had Tn to begin with, and then we had to figure out that I need to find out the value of n minus 1. We started backfilling the value, back substituting the value, and we found out what is t of n minus 1. Likewise, as a result, we got t of n minus 2. So we needed to figure out what is the value of t of n minus 2. And it led us to a condition wherein we had to find what is n minus 3. And after k iterations, k such calls, we generalized that we are going to end up into this particular situation. And we wanted to give an end to this one. And when this thing is going to end is when this thing becomes 1, because that is our base case. So this gave us this particular equation, and from this equation we found out that this thing is going to be 1 when k value is n minus 1. The same thing we replaced in this equation, and we reached to the conclusion that the time complexity is going to be big O of n, right? So I understand that this may not be very much intuitive like we had in the case of iterative program, right? Iterative approaches, but try to watch it one more time and probably practice on pen and paper. It will be much easier. And having said that, once we are done implementing a couple of more such examples, or rather solving a more such examples, it will become quite intuitive and easier down the line. Of course, you will not have to do all these things to figure out the time complexity. This is just to learn that when we say there is a time complexity of big O of n, what exactly does it mean and how do we calculate it in the case of the example being solved, regardless of the fact that this is iterative or recursive. So I'll stop my rant over here, and next we will try to solve one more problem using this method and see how we are going to make use of the back substitution one more time. Now let's take a look on this example. So here what we have is a function. There is some algorithmic implementation inside this function, and what it's going to lead to is this recurrence relation, wherein time taken to execute this for an input size n is going to be n plus t of n minus 1, and this is for all such n's whose value is greater than 1. And the base condition is when n value becomes 1, then we have the value as 1, right? So there could be some algorithmic implementation, so that we are not worried about as of now. Essentially, we need to sort of distill everything to the recurrence relation. So that is the reason we are seeing the recurrence relation itself. So given such a recurrence relation, how exactly are we going to figure out the time complexity for this. So again we are going to follow the method of back substitution. So let's do that. So since we need to figure out what is the value of n minus 1, so we will try to find out the same. So we have t of n minus 1 and we place the n value as n minus 1 here. So it becomes n minus 1 and this becomes t of n minus 2. Now we found out that we need to find the value of t of n minus 2. So we will find the value of n minus 2. We will place n minus 2 in place of n here. So that would be n minus 2. So we place the value of n here with n minus 2. So that is n minus 2. And we place the value of n as n minus 2 here. So that would be n minus 3. Right? And now what we can do is we can place this t of n minus 1 value back to this one. So when we do so, what we have is t of n is n plus n minus 1 plus t of n minus 2, and we can place the value of n minus 2 here from here. So that would be n plus n minus 1 plus n minus 2 plus t of n minus 3. What we can see is there is a pattern. When we have n, we are writing n minus 1. When we have minus 1, we are writing n minus 2. And we have minus 2, we are writing n minus 3 in the next one, right? So we could write this using this pattern like this. So n plus n minus 1 plus n minus 2 plus n minus k plus t of n minus k plus 1. Let me write it somewhat clearly here. So let me get rid of this one. Dot dot n minus k and t of n minus k plus 1. And when does this stop? Because eventually our goal is to get rid of this thing completely. We don't want to keep on calling this thing again and again. And in order to ensure that this thing is going to stop, we need to hit the base case. And when do we hit the base case? We hit the base case when we have n as 1 and the value becomes 1. So essentially t of 1 as 1 is the base case. So for that to happen, this value should be 1. That is n minus k plus 1 is equal to 1. So let's find the value for k. This is certainly n minus k minus 1 as 1. We can take the k this side and bring 1 on this side. So this will be n minus 2 equal to k, or k is n minus 2. So for this value, that is k is n minus 2, we are going to reach the base case. We are going to hit the base case and eventually all of this will stop. So now that we have found out the value of k, let's start to put this value in this equation. So n plus n minus 1 plus n minus 2 plus n minus n minus 2 plus t of, anyway this is the one that we found out, so this is going to be 1, and let's solve this. So this will get cancelled and this will become plus 2. So what we have is n plus n minus 1 plus n minus 2 plus 2, and this is anyway 1, right? So if you pay attention from this side, what we have is nothing but sum of first n natural numbers. And how do we represent this? So we represent this as n into n plus 1 by 2. So as we saw earlier in the video, that whenever we have such case, so for example when you multiply this is going to be n square by 2, then n by 2, then the leading term here is of course n square, and the leading term is what we take when we have to represent anything in terms of the big O time complexity. So this will be big O of n square. So for this recurrence relation, the time complexity that we have is big O of n square. Now let's solve some problems using the recursion tree method, and in order to understand the recursion tree method, let's take a look on this recurrence relation. So we have t of n, and this is going to give me 2 of t of n by 2 plus some constant time c, and this is going to have when n is greater than 1, and when n is equal to 1 the value is going to be c. So this is my base case. So in the previous section we saw that we could use the back substitution method, but in this one we will see the recursion tree method. What we understand is when we do some constant time of work, or rather when we do some constant work that is c, or that is going to take c time, we are able to divide the task into two tasks of n by 2 capacity. So we could represent the same using the tree, and that is the reason the name is the recursion tree method. So we have c, and then we have t of n by 2, t of n by 2, and again if we are able to do some constant time of work here, then we are going to divide it in two more subtasks. So let's say we do the constant time of work here, then we are going to divide it into two more subtasks, which is t of n by 4. Why n by 4? Because the actual work was n by 2. So we will do the same thing for this node as well, which is going to be a constant time of work, and t of n by 4, t of n by 4. And again we can do the same thing for all these nodes, like we can do a constant time of work, and then we could divide it as t of n by 8, t of n by 8, and it would be same for all these nodes as well, that is t of n by 8. So you get the idea. But the problem here is that we want to stop it at some point of time. We could not be doing it forever. We need to stop it somewhere. And when do we stop it? We stop it when the value of n is 1. So when this value of n becomes 1, then we stop it. So before finding out that when does this value become 1, let's figure out what is the amount of work we are doing on each level. So on this level we are doing c work, on this level we are doing 2c work, on this level we are doing 4c work, on this level we are doing 8c work. So basically when we replace this with the constant work, then we will be getting two more subtasks, that is the value n by 16, and eventually that would give us a constant time of work that we have done to split the task into smaller subtasks, right? So we get this kind of work that we are doing on each level, and when do we stop it? We stop when this becomes 1. And what does it take to this become a 1? So the way we could represent this is t of 1 is equal to t of n by n. What it means is it's as good as writing n by n to represent 1. And eventually when we have a layer wherein we are getting the task nodes as t of n by n, t of n by n, and so on and so forth. So at that level we will be doing nc work, right? Because here we were doing it like t by 2, then we did 2c work, we were doing t by 4, we did 4c work, here we were doing t by 8, here we did 8c work. So here we are getting n by n, so we will be doing nc work. So the total amount of work that we will be doing is c plus 2c plus 4c plus 8c plus nc. Let me write it here. So we can take the c common, and we could write this as 1 plus 2 plus 4 plus 8, and so on and so forth. The way it looks like is it's increasing in terms of 2 power right? So we could assume that n is something like 2 to the power k, and when we have this assumption, we will be using it later in the calculation. But for now, what we could observe is this is a geometric progression wherein the initial value is 1 and the final thing is 2 to the power k. And since we have the final thing as 2 to the power k, the total number of elements is k plus 1 and the common difference is 2. So using the formula for geometric progression, we could write this as 1 multiplied by 2 to the power k plus 1 minus 1 divided by 2 minus 1, and this would be c multiplied by 2 to the power k plus 1 minus 1. And since we saw that n is 2 to the power k, 2 to the power k plus 1 is going to be 2n minus 1, and eventually we could represent this as big O of n. So I understand that for some of you this may become too much mathematics, too much mathematical kind of an exercise, but the core idea behind this whole video, this whole section, is to get a hang of or the feel of what exactly does it take when we say that the runtime complexity or the space complexity of an algorithm is something. We should not be just doing some sort of superficial task and work. Rather, we should be understanding it in much depth and what it takes to derive the time complexity. Of course, when you are doing a DSA interview, or maybe you are solving some problem, or let's say if you are implementing some algorithmic task in your day-to-day work, then you will have a better idea of what is the time complexity like by just looking at the code. But there could be such scenarios wherein the code structure or the way in which the algorithm is getting implemented would be very much different. So in those cases, you should be in a state, you should be in a position to derive the exact time complexity, and that makes you a better engineer, right? And that is what we are learning right now. So what we learned here is that we were able to generalize this using a recursive tree, and this is the amount of work we were doing on each level, and effectively this led to this particular equation, and we were able to derive that since it's increasing in terms of 2 to the power k, the final thing is 2 to the power k, and the runtime complexity is big O of n. So now let's solve this problem, and the recurrence relation that we have here is we have t of n, and then we have 2 of t, n by 2 plus n, and this we have when we have n is greater than 1, and at some point of time we will have 1 when n is 1. So this is our base case, and this is the normal recurrence relation. So let's represent this in terms of a recursive tree and see what we have. So to begin with, we have n, and when we do n work, then we are able to divide the task into two smaller tasks of size n by 2. So we have n by 2, we have n by 2, and when we do n by 2 work, that is this one, then we are able to divide this into smaller tasks of n by 4, and likewise here as well we will have n by 4, and when we do this task, then we would be able to divide it into n by 8. So you get the idea. Here as well we will have n by 8. Then of course we don't need to, or we don't want rather, to do this forever. So at some level, on some layer, we want to be in a state wherein we have n as 1, because that is our base case. So the intended state is t of 1. Here we want everything to be t of 1. So let's also find out what is the work that we are doing on each level. So on this level we have done n work. At this level we are doing n by 2 but twice, so that again is n work. At this level we are doing n by 4, and that is 4 times, so that of course is n work. And likewise here as well we are doing n work, and here we are doing this n work as well. So we can see that each and every level we are doing n work. But the question here is, in order to find out how many times are we doing this, or what is the overall work we are doing, we need to find out what is the level, what is the depth, or what is the height of this tree, and how we can find it out. Let's try to find a pattern here. So on this level we have n by 2 to the power 0 work, the work that we do to split a task, and on this level we are doing n to the power, or rather n divided by 2 to the power 1. So this is the task we are doing in order to divide the task further, and then we have n divided by 2 to the power 2, then we have n divided by 2 to the power 3, and so on and so forth. Finally we will have n divided by 2 to the power k. So what we see is our depth is k plus 1. So 1, 2, 3 k and 0. So basically our depth of the tree is k plus 1, and since we are seeing that n is 2 to the power k, so what I mean to say is we want to be in this terminal state, right? That is my base case. And when do we reach the base case? When we hit this condition. And effectively this is as good as writing. So basically this was represented by this was represented by this was represented by this was represented by this, and likewise what we have here is 1, and this is represented by 1. So what it means is n is 2 to the power k, right? And when we have n as 2 to the power k, what is the value of k? It's log of n to the base 2. So now that we have k plus 1 levels, what we can do is we can substitute this k value with this. So we can have it as log of n to the base 2, and at each level we are doing n work. So let's multiply this, right? So this is the level, and at each level we are doing the n work. So the total work that we are doing is n multiplied by log of n to the base 2. And what do we have is big O of n log n. So big O of n log n is the time complexity for this recurrence relation. So let me write it here, n log n. And this is how we were able to find out the time complexity using the recursive tree approach. So I hope this might have given you an intuition, an idea regarding how exactly we could make use of the recursive tree to find out the total amount of work we are doing. So this would be the last sort of example into the part of the video where we were finding out the running time complexity for either iterative or the recursive algorithms, and the overall idea was to provide an intuition using which you should be able to solve any other problem. And I am hoping that this might have given you a solid intuition regarding the approach, regarding the method that we follow. And if there could be just one takeaway, that would be like, in fact, there could be two takeaways. So the first one is that effectively you want to find out the amount of work that is being done that you need to figure out. And the second thing is this amount of work needs to be represented in terms of the input size. So let's say if the input size is n, then this needs to be represented in terms of the input size. So eventually when you find out the amount of work that is being done and how it's related to the input size, that is going to lead you to find out the overall running time complexity, which in most of the cases is going to be represented by big O notation. So with this, let's move to the next section where we will be doing some analysis around the space complexity, and there as well we will solve a couple of problems and see how we can find out the space complexity for a given algorithm. Now let's learn how we can do a space complexity analysis. And of course, as we saw earlier, that an algorithm could be either an iterative one or a recursive one. So to begin with, we will be learning the space complexity analysis for the iterative algorithms. So here is one example that we have. So we have a function f that is accepting two parameters. The first one is an integer array or whatever array, that is a, and its size is n. There is a variable I, and for I as 0 to n minus 1, what we are doing is we are adding 1 to the value of array at index I. So essentially, if you look, these are the couple of variables we have. So we have I, we have the array, and then we have the n. So a and n are supplied by the input itself. So as a thumb rule, whatever is supplied as part of the input, those things are not considered in the complexity analysis, space complexity analysis. So what do we have extra than the input? The extra that we have is this variable, that is I. But please note that this I is not going to depend on the value of n. So it does not matter that the size of array is 1 or maybe 10 or 10 lakhs. It's not going to depend on that particular value. So the space taken by the variable I is always going to remain the constant. So such things are called as constant space, and this could be represented as C. And in this particular code section, we don't have anything that is going to take extra space. So for this particular code, for this particular function, the space complexity is big O of 1. So big O of 1 is something that we use to represent the constant complexity, and in this case this is a space complexity. So this is a constant space complexity. Now let's move to the another example. Here again we have a function called as fun. It's accepting two things in the parameter. One is an array A and the size of the array is n. Again we have a variable I that is not, of course, depending on the input size. So this is going to be a constant thing. And here what we see is we are creating a new array. So we are creating a new array B, and that is of the same size of the input, that is n. And in this code block we are writing simply the value of array A at index I, incrementing it by 1 and placing that in the array B. So here we are creating an extra array that is of the same size, and that is proportional, that is dependent, that is related to the size of the array. So if this thing is going to increase, so let's say if the initial value of the array is, initial size of the array A is 10, then the size of the B array is also going to be 10. If it's going to be 10,000, then this size is also going to be 10,000. So this is depending on the input size of the array A, right? So in such cases we represent the space complexity or the space it's going to be taking is big O of n, right? So basically n is the input size, and we are creating a new array of the same size, so its time complexity is big O of n. So what would have happened if I were to create a new array? Let's say I omit this closing and I create a new array. So let's say I create a new array, let's call this as C, and this is also going to be of size n itself. So the basic principles would be the same that we have seen in the case of the runtime complexity. So this is again going to take a space complexity of big O of n, and these two arrays are not dependent on each other. So C is independent of array B. Then in that case, that's going to give us effectively big O of n plus big O of n space complexity, and we take the most prominent one, the most dominant one, which is n, of course. So the overall space complexity is going to be big O of n. Now let's see another example. So in this example, what we have is function fun. We have an array A and the size is n, and we are creating an array B that is two-dimensional, and this is of size n cross n. So if A was like this, like let's say if it was of size 4 and if this was A, so what we are doing is we are creating B that is of size 4 cross 4, and this is array B. Of course we have constant constant space taking variables I and j, those are not going to lead to any sort of a space complexity, right? And the only thing which is going to lead to the space complexity is this particular array that we are creating, the new extra array that we are creating, and this is of size n cross n. And if the input size is n, this is going to be n square. So let's say if this was going to take 4 cells, this is going to of course take 16 cells. So how do we represent this? We tell this as the space complexity is big O of n square, right? So I think you get the idea. So finding out the space complexity in the case of iterative programs is fairly easy, and the overall end goal is to represent what is the space that is going to be occupied by the new data structures that we are creating other than the input ones, right, in terms of the input size, that is the n. And once we have figured that out, how it's going to be correlated to that, how it's going to be related to that, that is going to give us the space complexity. Now let's move forward and do some analysis around the space complexity in the case of recursive programs. Now let's learn about how we can analyze the space complexity in case of the recursive problems. So here we have a problem. So we have a function fun, and it's going to expect, let me correct this. So this should not be a, rather it should be n. So it's going to expect n as the input parameter, and if the value of n is greater than 1, then we are going to call function with value n minus 1 recursively and print the value n. So of course this is a recursive call, and how exactly can we figure out what is the space complexity? So there are a couple of ways, one of which is the tree method. So basically what we try to do is we make the recursion tree, and using that we try to evaluate the space required, the space complexity. So let's see the tree method. So in order to simplify the representation, I'll represent fun with the letter f. So let's say I have f, and assume that the initial value of n for which this is called is 3. So there are two things which are happening. So first thing is of course the call, right, to the recursive method itself with the n minus 1 value, and the second thing is we are printing the value n. But before that we are checking if the value is greater than 1 or not. So 3 is of course greater than equal to 1. So what we will be doing is, first of all we will make a call with f2, and this will be printing the value 3. Then 2 is definitely greater than equal to 1, so we will be making a recursive call as f1, and then this would be printing with value 2, and 1 is definitely greater than equal to 1, so this will be making a call to f of 0, and this will be printing 1. So now if you see closely, 0 is of course not greater than equal to 1, and this is where the recursion is going to stop. So how do we analyze the recursive tree? Well, the method to analyze this is to start from the root node and try to go down, left, then right. So we are starting from here, and we will be going like this, we'll be going like this down, then we will be covering the left one, then the right one, and then we will be coming back. So this is the way in which we usually try to cover the recursive tree. So let me undraw this one and then probably use a different color so that I could represent it in much better manner. So there are two things which are going to happen. First is of course we are going to traverse the tree, and as and when we are going to encounter a recursive call, for example wherever we are calling f of something, we will be putting that value in a stack. Why stack? Will come to the intuition in some time, and as soon as the execution of that particular recursive call is completed, we pop that entry from the stack, and essentially the stack leads to the space complexity in the case of the recursive programs. So let's start the analysis. So I start from here, and at this point I see that f of 3 has been called. So I will have a stack to maintain this particular information, and to begin with we have to push f of 3 to the stack. Of course, this is not going to be looking like this in the actual implementation under the hood. Rather, what we will be having is there would be some sort of function pointer, right? So some sort of guideline to the compiler or whatever is the underlying mechanism that your execution was done for this f of 3, and it got halted because you had to call f of 3 recursively. So what I mean to say is, let's say you started for f of 3 and then you came here and you did not complete the f of 3. So completing would have meant that you executed this entire block, but this will not be the case. You will come here and then again you will call with f of 2. So that is what is going to happen, right? So in that case we pushed the f of 3 so that we could track it later on, and then we move to the other function call, that is f of 2, and this is how the tracking continues. And we see that we have encountered f of 2, and this is what we are going to push to the stack. Then we come to f of 1, and we will push this to the stack. Then we come to f of 0, we push this to the stack, and finally at this point of time we are going around this, and this is the last time that I'm going to encounter this particular f of 0. It does not matter that this is going to be used somewhere else or maybe occurring somewhere else in the recursive tree. For example, in this example, surely f of 0 is going to be there just once, but in some examples this could be repeated, right? So that is the reason I was saying that this particular f of 0, it is the last time that we are encountering it, and whenever that is the case, then we pop that entry from the stack. So in terms of representation, when you see the first dot for a function call, that is the point at which you push to the stack, and when you see the second dot, then you push out from the stack or pop from the stack, right? So that is what we have done. Now we are going back to the f of 1, and we will be coming to the print statement, and we will print the value 1. Now I go back to the f1, the caller, and this is the last time I am going to see f1, so I will be popping it off. I go to the f2, I come to the p2, so p2 is going to lead to printing of the value 2, and this is where I come now, and this is the last time I am going to encounter the function f2. So f2 is popped off from the stack. Likewise, we are at this particular point wherein we are going to print the value 3, and then we come back to f3, and this is the last time that we are going to encounter f3. So f3 is also popped off from the stack, and this is where our execution completes. This is where the recursion tree traversal completes. So if you notice, these are the entries that we are going to have in the stack. So at maximum, it's going to take 4 entries. So let's try to see if we are able to find some sort of correlation. So if you look very carefully, this is nothing but the number of the recursive calls that has been done in your call, in your recursive method. And why so? Because we are calling f0, f1, f2, f3, so and so forth. And that is what we are going to maintain here. So it's f0, f1, f2, f3, and so forth. So for a given fn, how can we find the recursive calls? That would be done, right? So if you look very closely, for f3, we are calling it like 1 time, 2 time, 3 time, 4 time. So for f3, we are calling it 4 times. So there are 4 recursive calls. To calculate f2, we are calling 1, 2, and 3. So for f2, we have 3 recursive calls. For f1, we have 1, 2, two recursive calls. So if I were to say that in order to calculate fn, I have to make n plus 1 calls, that would be the correct statement, right? So essentially, the height of the stack or the depth of the stack or the maximum capacity at which the stack will be filled would be n plus 1 if my input is n. And let's assume that each of the cell, each of the entry in the stack is going to occupy, let's say, C, that is the capacity. So C is essentially going to be constant. So it does not matter for which n you're calling it, it's always going to occupy the same space, more or less. So essentially we have Cn plus C, and C of course is the constant. So anyway, the leading term here is Cn, and C is constant, so we could ignore it and we have n. So effectively, this particular algorithm is going to take this particular space, that is big O of n. So the space complexity for this algorithm is what? Big O of n. So this is how we were able to find out the space complexity for the given recursive algorithm. So what we did is, first of all, we draw the recursive tree, we try to populate the stack, the recursion stack, and we try to find out how exactly the recursion stack would be dependent on the number of the inputs or the input size. And this is the correlation we had, and this is the space complexity we got. Now let's solve another problem, and again this is a recursive problem, and the question is to find out what is going to be the space complexity for this one, right? So again we will follow the same tree method, and we will create the recursion tree, and we will try to find out the depth of the stack. So let's start by creating the tree. So we have 3 to begin with, so let me write it in center. So we have 3 to begin with, and this thing is not less than 1, this is certainly greater than or equal to 1. So we will make the first call, that is f of 2, and then we have the print statement, that is print of 3, and this is going to be f of 2. So we are calling f of n minus 1 twice, first in the beginning, then we are printing the value, and then in the last. So f of 2 is going to call f of 1, print the value 2, and then it's going to call f of 1. Print of 3 is of course not going to call anything, and function 2, f of 2, is going to call f of 1, it's going to print 2, and this is going to call f of 1. Now f of 1 is going to call f of 0, it's going to print 1, this is going to call f of 0, this is going to call f of 0, this is going to print 1, this is going to print f of 0, and this is f of 0, print 1, this is f of 0, so this is again going to be f of 0, this is print 1, this is f of 0, and when it hits 0, that is where we stop the recursive calling, and this is where all this tree stops. So let's count how many times are we calling the recursive method for a given number. So for f of 3 we are counting it like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So for f of 3 we are calling it 15 times. For f of 2 we are calling it 1, 2, 3, 4, 5, 6, 7. So for f of 2 we are calling it 7 times. For f of 1 we are calling it 1, 2, 3. So if you see the pattern, this is nothing but 2 of to the power 4 plus, or in fact it's minus 1. So it's like 16 minus 1. This is 2 to the power 3 minus 1, that is 7 minus 8 minus 1. And this is 4 minus 1, which is 2 to the power 2 minus 1, which is nothing but 4 is 3 plus 1, 3 is 2 plus 1, 2 is 1 plus 1. So 3 and 3, 2 and 2, 1 and 1. So essentially f of 3 could be written as 2 to the power 3 plus 1 minus 1. And likewise, we could write the number of recursive calls that would be required would be 2 to the power n plus 1 minus 1. So like we saw in the previous problem, can we simply say that the space that is going to be needed is going to be this much? Is it going to be the order of 2 to the power n plus 1? Well, let's find it out. So let me erase this part, otherwise it will become difficult to explain. So let me erase this part. So one thing is for sure, that in order to evaluate f of n, we need to call these many times, right? And now let's track this particular recursive tree and try to find out how many times or in what manner are we going to populate the stack. So let me change the color here and let's create a stack here, and we will follow the same recursive approach, the recursion tree tracking approach or the traversal approach that we did in the previous problem. So we come to F3, we push to the stack, we come to F2, we push to the stack, we come to F1, we push to the stack, we come to F0, we push to the stack. We see F0 for the last time, we pop it off, we do the printing and everything. We see F0 for the first time, you push f of 0 to the stack. We see f of 0 for the last time in the stack, so we pop it off. Now we come to f of 1, we see it for the last time in the stack, we pop it off. And then we print the value 2, we come to f1 and we see f1 for the first time, we push it to the stack. Please note that this f1 is different from this f1. Right? So this is what I was trying to say in the previous section when I said that these function calls could be repeated. So essentially this f1, this function call is different from this one, and that is the reason we had pushed out f1, we had popped off f1, now we are pushing it in, and this one is totally different. Anyway, so now we go to the f of 0 and we are seeing f of 0 for the very first time. And this f of 0 is different from these two ones, right? So we push to the stack and now we see this f of 0 for the last time, we pop it off, we traverse, we print p4, we see f of 0 for the first time, this f of 0, we push to the stack, now we see this for the last time, we pop it off, we come to the f1, we see this for the last time, we pop it off. We come to the F2, we see this for the last time, we pop it off. And likewise, you could try to traverse the entire second half of the tree yourself, and what you will find out is eventually at each and every level, we are going to push the given function call, and once that is completed, we are going to pop it off. And in the last, everything will be popped off. So there are two interesting observations here. The first one is that this level or this particular entry in the stack is always occupied by f of 0. This one is always occupied by f of 1. This one likewise by f of 2, and this one likewise with f of 3. So what do we have? What we have is that even though we were seeing that we have to make these many calls in order to calculate the value of fn, but the number of actual elements or the depth of the stack that we are going to need is only going to be this much, which is pretty much less than this value, right? So if I were to calculate f of 3, then I would have to make 15 recursive calls, but all those recursive calls could be tracked using only 4 cells. only these 4 cells, right? So what we see is that the depth here is nothing but the depth of the tree, and the depth of the tree here is n plus 1, right? So if we have 3 here, then it's like 1, 2, 3 and 4. So the stack depth could be written as on the order of n plus 1. And let's say each and every cell in the stack is going to need a capacity C. So this could be written as NC plus C, and NC is the leading term here. So in that case, we could say that the space complexity that is going to be needed for this recursive function is big O of n. So even though we had to make these many calls, the space complexity is not in the order of big O of 2 to the power n. Rather, it's just going to be big O of n. So as a good rule of thumb, let me write it here maybe. Whenever we are dealing with recursive methods, recursive implementations, then your space complexity is always going to be defined by the depth of the stack. So stack, by the very nature of it and the way in which the recursion works, it ensures that it makes the very optimal use of the stack space. So for example, as we saw here, that everything that is f of 0 is going to be occupied or is going to be placed in this particular cell itself. It's not going to happen that f of 0 could be here and then it could be here and then it could be here in other cells as well. Rather, it's going to be reusing the same space, and that is the reason the effective space complexity is going to be the depth of stack. So whenever you are tasked with finding a space complexity for a recursive method, all you need to do is try to find the recursive tree and see if there is any pattern, and based on the pattern try to find out what is the depth of the stack. And of course, each of the cells is going to be taking a constant capacity C, and the depth of the stack D, whatever you have in terms of your input size, is going to lead to the effective space complexity. And that's about finding out the space complexity of recursive methods. Now let's learn about the ordering of asymptotic complexities. As we saw earlier, that all the asymptotic complexity, be it the runtime or the space complexity, it could be represented as some sort of function that we were placing in the big O notation. So the idea is to learn what is their ordering, as in which one is better and which one is worse, right? So let's start with the best one. So the best one is big O of 1. What it means is that this is constant time. So constant time is, let's say if there is a algorithm that is like this, and this is going to take some sort of input n. So it does not matter if the value of n is 1 or let's say 1 million, the time taken by this algorithm is always going to be, let's say, t seconds or t milliseconds or whatever, right? So basically the time taken to execute, to run this algorithm is not going to depend, is not going to change with the change in the input size, the input value rather, right? So this is what we mean by the constant time. This is the most desired and the least practical asymptotic complexity. So essentially you get the idea. Everyone desires to have this kind of asymptotic complexity, but this is very not practical to get in for most of the practical use cases, or most of the use cases rather. But anyhow, moving on. The next one on the list is logarithmic time complexity, which is represented by big O of log n. So this one is worse than the constant time complexity. The next one on the list is big O of n. So this one is also called as linear time complexity or a space complexity, whatever you wish to use it for. So basically let's call this as asymptotic complexity. So this one is less better, or this is worse than this one, and of course than this one. The next one on the list is big O of n log n, also called as log linear time. So the next one on the list is big O of n to the power k, where k is greater than 1. So anything like big O of n square, big O of n cube, big O of n4, all these things, right? And of course these things are worse than big O of n log n, and with the k size increasing, for example k as 2, k as 3, k as 4, as k increases, the complexity becomes worse and worse. The next one is big O of 2 to the power n. So this one is essentially your exponential time, and the final one is big O of n factorial. This is the worst of the lot. So let's sum it up and let's have the final list. So this is the final list. Best one is constant time and the worst one is the exponential time, and everything is in the ordered list itself, ordered sequence itself, as in this one is better, this one is better than this one is better than this one is better than this one, so on and so forth. So another very important point to notice about this complexity is that these things are called as asymptotic complexity. What we mean by asymptotic complexity is, so let's say if this is the time axis and this is the input size axis, then as this value increases beyond the threshold, and most preferably a very large number, at that point of time how exactly your algorithm is going to perform, that is what we measure by the algorithmic time complexity or the space complexity, because essentially we want to measure the rate of growth. This is not an exact time taken, right? So we are not interested in finding out what is the exact time taken. Rather, what we are interested to know in is what is the rate of growth. So let's say if the rate of growth of my input size is something, then with that rate of growth, with that increased number of input size, how exactly is my runtime going to perform? So we want to have that sort of correlation, and that is what is represented. So for the lower values, whatever is this value is not very useful to us, is of use to us. So for example, let's say if there is an algorithm that is only going to be running on an array of size 10 and its time complexity is, let's say, big O of n square. So it does not matter, right? Because at each and every time we are going to just have like maximum of 10 elements in the array. However, it's going to matter if the maximum capacity of the array could be to hold, let's say, 100k elements. So I hope you get the idea. So basically, asymptotic time or a space complexity is always of interest when the value of input increases to a large size. So that is where we have the concept of asymptotes in the mathematics, and that is the reason we have this word asymptotic complexity. Thanks for watching the tutorial. I am very positive that you would have found the content helpful. So what's next from here? I would suggest to start applying the concepts that you learned in this video in each and every piece of code that you are going to write, be it a typical data structures and algorithmic problem solving, or some code which you write as part of your daily work. With enough practice, deriving the asymptotic complexity of any code will become a cakewalk. So with this, now I request you to support my work. Creating a thorough and in-depth video tutorial like this involves many parts to it. For example, brainstorming the topics which are to be covered, researching on the topics by reading textbooks, finding questions, recording the video, editing, etc. etc. Doing all of this took me around 50+ hours in total, and doing this with a full-time job was not easy, but I loved every moment of it, and I sincerely believe that you gained some valuable knowledge from this video. So if you did, support my work by liking this video and sharing it with others who might be interested in learning this concept. Also, do let me know in the comment section if you have any questions or queries. I'll make sure to respond to each one of you. I have extensive plans to make even more in-depth tutorial videos, so please subscribe to the channel and hit that bell icon to get notified as soon as I upload a new video. So that shall be it for this video, and I'll see you in the next one.